Everyone to session 5, transmission and interconnection. We're about ready to go ahead. So if you want to come in, take a seat, grab your drink, and we'll get started. So I'd like to introduce Josh Novacheck, who is taking the place of Debbie Liu. Debbie got sick and is not able to be with us this week. So Josh very graciously agreed to step in and to chair the session. So I appreciate that very much. Josh is an old friend from NREL, back from all of the wind and solar study integration days. Now he's doing big transmission stuff at the NextEra. So let me turn it over to Josh.
Great. Thanks, Charlie. Glad I'm able to come in and be here, but definitely miss Debbie, but hoping that she starts feeling better soon. So we've got a great panel today talking about transmission and interconnection. We'll start with Babak, who's going to start us off, kind of talking about some lessons learned from IBR grid interconnection studies, and then we'll kind of slowly transition to kind of domestic discussion of queues and what are some of the solutions to the bottlenecks that we've encountering. So with that, I'll turn it over to Babak.
Thank you very much, and thank you for having me again. So as I was mentioning in my earlier presentation, some of the points that I wasn't able to cover, I'm covering here, but these are basically a collation of very different practical experiences. And I initially had 3 more, but because of time, and hopefully I can comply with 18-minute requirement, I have actually deleted 3 case studies. So what brings all these case studies together? Like I said, different technologies, different power systems, but the only commonality between all these is that they are real projects, real power systems, and real OEM model or performance, if you like. Starting with the first one, which is the IBR operation under low system strength conditions, basically low or very low fault level. The particular example I have, it's for wind farm. I don't discuss, why wind and nothing, basically single out wind, basically. But I'm happy to take that as a question rather than discuss the differences between wind and other technologies. So I think I might have presented this in like ESIC 2019. So that was basically reflective of the one of many regulatory changes that we have after Australian blackout in 2018, which is basically on system strength assessment and system strength remediation. I've written quite a few different things. I'm not going through each one of them. Essentially, how I can classify these solutions into 2 categories, basically. At the left-hand side are basically the solutions that install within the connection point of a generator. And as such, it is owned and implemented by the developer. And at the right-hand side are a suite of solutions that's implemented by the network owner, and as such, owned and implemented by them, basically. And I should also highlight the last point on this slide. The color coding is intentional, meaning that and this is based on the degree of popularity, if you like, or how they have been adopted. So those highlighted in green are the most popular ones, and those in red have not been adopted, basically. So this is basically just a recap of where we were until earlier this year. I'm just repeating the same thing I had in the previous slide. Now the color a little bit changed, or maybe let me highlight 3 basically differences or experiences over the 5 years until we come to March 2020, which I will discuss in a second. Basically, you can see that the color coding for some of them have changed, basically, namely the very last one at the bottom left. So contract with other generators, that's gone. So in 2018, as I was showing you, that was possible, but not very widely adopted. So that's gone. In 2018, grid forming technology and namely battery were in infancy, basically. The experience has been quite different after 5 years. And that's why I highlighted that, again, the next one up, that is not just synchron, but we have grid forming. And I will, in the next slide, present you different types of solutions, not in terms of technology, but how they are connected to the wider power system. So let's basically recap this until March this year. And then what basically else come in, excuse me. Okay, so from 15th of March this year, a third element, which is somewhere in between, that refer to as system strength charges. So these are basically in Australian national electricity rules. And based on that, then AEMO will need to adjust and redetermine their requirement, which is system strength impact assessment guideline, something that I myself very last minute was involved to basically help AEMO. And I will discuss what the problem was or has been basically. Okay, so what this system strength charges are is a product of three factors. The first is obviously the dollar basically, so that the network owner will need to determine. The second one, they call it system strength locational factor, which is an electrical distance between the IBR connection point and a set of predetermined nodes at which, if you like, system strength is calculated. And the last, which is the most controversial one, is the system strength quantity or SSQ, basically. I will talk in a second what this system strength quantity is. But before that, let me just summarize the current state of play in terms of what solutions are available to basically address system strength issues or instabilities that are identified. And I have actually classified them into three categories. So I'm going to discuss briefly about each. But again, I have also used color coding against each type of solution. Again, intentional, the one which only have one in green is the one that most feasible, if you like, not the most desirable. And those in red have some challenges that it's unlikely to be adopted, and doesn't mean that technologically they are inferior. Starting from the left-hand side, the first solution is to install a synchronous condenser or grid-forming battery in the wider network. And the use of grid-forming inverters is not possible because network owner cannot basically own assets that generate megawatt. The use of Syncon has been there previously, but unfortunately, and that's one of the concerns with this system strength charges, that we have projects, let's say 400 or 500 megawatt, and the annual charge of essentially borrowing system strength capability from network has been provided like $12 million to basically our client, which means that if you multiply that by 30, again, $360 million, which is more than the cost of the project itself. And then in between, we have solutions that co-located, meaning that are inside the connection point, and something which is not basically, it's not basically proud, but we back to maybe 5 or 6 years ago, the solution that highlighted in green is basically a solution that we wanted to avoid to begin with, which is an embedded synchronous condenser. But because of issues associated with other solutions, many of which are price related, some regulatory related, this is the one that is most attractive currently. And then the last one to the right basically is a solution that is not inside the connection point, but in immediate vicinity of the connection point. And again, that can be a synchronous condenser or grid forming battery. Syncon is not used because that's essentially an inferior version of the one that I was showing you at the left-hand side. Grid forming battery, I mean, I haven't highlighted in green, but I currently have 2 projects that developer trying to implement this solution. Okay, so let's talk about some of the challenges I mentioned with this system strength quantity and the new framework. The previous approach we had in Australia until earlier this year was that the need for system strength assessment and the potential remediation is determined based on a preliminary assessment. And if a full assessment is identified, the basis of which is wide area EMT simulation, that's only if the wide area simulation shows a genuine instability, then the developer would have needed to install a solution. Now, moving into the current approach, basically, that's unfortunately gone. And instead, we have this formula that you basically see it here. Is essentially a reduction in the fault level available in the power system based on this formula, which what it tells you is that if the SCR with the stand capability of generating system, which is determined by SMIP EMT studies, is 1.2 or below, that number will be positive, therefore no remediation is required. But in reality, the vast majority, if not almost all of grid following inverters don't have such a withstand capability, meaning that this number comes negative, meaning that a remediation is required, or otherwise they need to opt in paying system strength charges, which in some of the regions are extremely expensive. I gave you an example. And based on this basically deficiency, and especially with the second formula on SSQ that I've put here, just less than a month ago, AEMO submitted a rule change to AEMC, Australian Energy Market Commission, for this rule change. So that's only basically going to reduce the system strength quantity, which means that it would be less of system strength charges. However, still the problem exists that the solution that previously was only to be implemented based on studies, this is now based on a preliminary assessment. Okay, moving to the second basically case study. So this is grid forming inverters. I have one for medium, what I call medium system strength condition, and then the next one for low system strength condition. Starting with the first one. So for those of you that attended ESIG last year, I had this presentation, just a recap, and I normally don't tend to copy and paste the slides from previous years, but I'm just using this to build foundation, and I'm making a little bit changes. For those of you that didn't join this presentation last year, color coding, again, intentional, the basically capabilities or services, whatever you like to call, highlighted in green are those that are common or mostly required by different grid codes, and namely in Australia for whether it's grid forming or grid following inverters, and those that highlighted in orange are the additional ones that typically attributed only to a grid forming device. Okay, now I'm changing the color coding. So here, and I should admit, actually, I've made one change. So the boxes that we had in the previous slide subtly changed. So in the previous slide, I called everything damping. Now this year I have actually classified that to electrical damping and electromechanical damping. Reason being is that the control system and control loops, excuse me, and the placement within the cascaded control system of grid forming inverter are coming from very different parts. If you want to provide electrical, electromechanical damping, nothing else changed. By color coding here, I mean those that highlighted in red are the least required or desired, and those that highlighted in green are most required. And part of this is with important recognition that you cannot realistically get all these capabilities or services from the same device, same project simultaneously. That's simply impossible. So it's going to exceed the capability of a grid forming inverter, and that's not control capability, the current rating. Okay, so now this slide is a little bit congested, but I didn't put it here for you to read every single line. This is based on a real assessment that I have done for one of the clients on choosing grid forming batteries for a fleet of their projects, basically. And the reason I put this under medium system strength condition is because some of those additional challenges that I will discuss a little bit later when it comes to weaker part of network are pretty much segregated. So you can see that the color coding is very different. And since then, this is now with 8 OEMs, been amended to 11 OEMs, but you can see that there are quite vast differences between capabilities, basically. Some of the points maybe I highlight. One is the switchover during FRT that's happening on quite few of the makes, but to me that's negate the purpose of why grid formation was required. To begin with, maturity of simulation models that remain concern both EMT and in particular phasor domain from some of the providers, and so many other capabilities. And I should apologize in advance. The slides that you will be getting as distributable will not have this various slide, because I think if someone works, I think these basically OEMs can be reverse engineered. So you will not see this, unfortunately, in the distributed slide. Okay, so let's highlight what are the differences when we go under low system strength condition. So there are some of the capabilities that I highlighted in red, and I would like to focus on inertia because that's one that most people are talking about in most countries, and almost becoming synonymous to what we otherwise consider a grid formation capability. The concern here again is due to partly the current limitation of device, and noting that inertia is a global quantity, it's not local quantity. You don't need to provide it locally, and just build on that a little bit. So this is real project, real simulation model. What would happen if under very low system strength condition, you would like to provide inertia? In this case, frequency changes, and the grid forming device, whatever the inertia constant is, programmed to provide or emulate inertia basically, or whatever else you would like to call it. What happens here, there is no voltage disturbance at all. Remember, there is no faults, no changes in the voltage. But because under this low system strength condition, active and reactive power are very highly coupled, so as voltage and frequency, a change in frequency because of providing inertia or active power, excuse me, active power would result also change in voltage. And you can see that this is causing a voltage collapse. So should we be expecting to provide inertia under this low system strength condition? Moving to another case, this is based on a doubly fed pump hydro that we have had. And again, I'm not going through every single cell, but you will have every other slide in the distributed version. I try to compare this, and based on experience that we have gained, again, real project, real models, basically, I try to compare them with some of the parallels that we can potentially think of, and most notably with battery energy storage system. And as the title here highlights, I would like to be very clear. I'm not trying to generalize and saying that, you know, batteries, as you can see, are the best devices. We have to go with battery. This is only from a stability standpoint. Obviously, if you're talking about ongoing supply, these devices and whether it's fixed speed or doubly fed pump hydro are superior. But I'm only focusing on the stability functions, if you like. One of the main differences between battery and doubly fed pump hydro, both are power electronic based devices, is the speed of response and this flexibility and not needing to switch over between modes to provide frequency response. And that's by far superior. And maybe again, I'm coming back to dynamic model maturity. I already spoke about that for grid forming capability. The thing is that if you have battery or solar or wind, you have so many of them, and they have been for so long that you know, initial stages of those models maybe weren't perfect, but after several years and decades and many projects every month, so those models have been evolving and you know, maturing. Whereas with pump hydro, you don't have so many of them. Certainly, we don't have many of them in Australia. So these models are not really following the same level of maturity that you will have from a battery energy storage, basically. And maybe the last point here is impact on system strength. So obviously, you can see that I changed color coding for battery. This is recognizing that with battery, you can have grid forming or grid following. And this is considering that, whereas with the doubly fed machine, it's basically a sink for system strength, if you like. Okay, so now moving to another technology. This is a DC coupled battery and solar. I don't know how many, if any, you have here in US, but I'm sure it will come very quickly. Historically, or maybe let me explain these topologies first and then talk about the comparison. So essentially what DC connection is about, with battery, most often, if not always, you have a DC converter, and part of that is because you want to have buck boost capability for quadrant operation as required for a battery. For solar, you don't need that. So the commercial models that we have seen could have a DC-DC converter for the solar inverter as well, which means that you use switching devices rated for lower voltages, or you can omit that altogether, and they're coming back one way or the other to the DC bus, a common DC bus, from which then you need to convert that back to the AC that connects to the network. Now, this is a comparison of different technologies that you can have. In Australia, again, I don't know how it works here. These days, it's not really financially viable for people to basically develop a standalone solar, basically. A standalone wind is still very viable. And because of that, AC hybrid to date has been the prime technology, if you like. But the DC technology offers two advantages. One is that it gives you now a potential for a fully dispatchable generator that you don't have that with AC hybrid. And second is more efficient. But what are the challenges? And again, I'm keep coming back, dynamic model maturity. So the maturity of dynamic models, and this is both for EMT and phasor domain, but in particular for phasor domain, that essentially how you're going to correctly model the DC in phasor domain simulation. Another basically challenge, we keep talking about grid forming capability. So with DC hybrid, grid formation is not possible. With AC is possible. It's not there right now, but it's not basically far from implementation. And because of these challenges, and this is basically work in progress, hopefully in 1 year or two would be very, very different because like I said, from efficiency, DC hybrid is definitely superior, but currently it's basically a solution that if a developer goes, they basically essentially taking the very high risk of delaying their project by a year or two. Now, this is the very last example I have. So now we're going a little bit off grid basically. This is basically energy island. It's in Australia. It's not in Northern Europe. So I basically show you briefly the single line diagram and different solutions that we have investigated. And maybe this is those of you that involved or heard of the project in Europe a little bit different. So it's perhaps inverse of that. In this case, there are, so first of all, the project size is like several gigawatts. Again, I cannot disclose the exact size because of confidentiality, but we are talking, huge, basically, islands with onshore wind and solar farm, basically. And we have assessed different solutions because the conclusion was that this option cannot work by itself with having wind and solar and electrolyzer, basically, that is used offshore. And both AC and DC options investigated. AC options were ruled out for a suite of reasons. I'm happy to take that as a question. And therefore, there is a need for auxiliary solutions. So we have put here grid forming battery and Syncon. I'll show you how they compare against each other. And this is basically the offshore side. Remember that these are like several hundred kilometers off the shore. So it's the hydrogen production facility and electrolyzer, namely. And like I said, the connection between the shore and offshore is with HVDC link. So here we have looked at different options because wind, solar, and electrolyzer, they all power electronic interface devices. It's not going to work, and HVDC is not going to work viably by itself. The solutions that investigated broadly, two categories, grid forming capability and use of Syncon, and a combination of these. So the one that, those that highlighted in green have been identified as the most viable options. Part of this is also technology maturity. So as you can see, options that don't have Syncon have been ruled out. Options, or at least have been assessed to be less desirable. And similarly, options with grid forming HVDC have been given a lower score. Some of this have been simulated using generic model, but not every single combination. So the conclusion is consistent with what is being presented here. And that's still our assessment or understanding in Australia that grid forming battery is much more mature than grid forming HVDC. And the options that have been shortlisted as the most attractive commercially and technically are the ones that have a combination of Syncons and basically battery, which meaning that we're not just relying on one device. Obviously, with Syncon only, you don't get frequency control, so that's definitely ruled out. But with grid formation only because of concern on current limitation that I mentioned, you are, and in this case, you do absolutely need inertia. You absolutely need inertia because this is a complete island. If a disturbance happens, someone has to arrest frequency nadir, which our assessment is that Syncons are more attractive, at least from a commercial perspective and readiness. And that's all for me. Thank you.
Next, we'll have Will Gorman from the Lawrence Berkeley National Lab come and present to us on some of their roadmap work, looking at how some suggestions for suggestions for clearing up some of the queue roadblocks that we're experiencing.
Okay, am I on? I think so. Okay. Well, great. Well, thanks for being with us here today. Thanks for the invitation from ESIG. My name is Will Gorman. I'm a research scientist at Lawrence Berkeley National Lab in the Electricity Markets and Policy Department, which is a group that puts out a lot of data products and market reports related to the integration of renewables onto the system. And as Josh said, today I'm going to be talking about a Department of Energy program called the Interconnection Innovation Exchange, where we try in one pillar of it to create a strategic roadmap to think through solutions and opportunities that we might have to unlock some of the queue backlogs that we've started to see, not just in the United States, but really across the globe. So a little bit of an outline of where we're going to go. So for those of you in the audience that are maybe familiar with some of our work, I am going to go through a number of graphics and data products that outline the status of the queues today in the United States and provide a little bit of our perspective of why we think there is some evidence of a problem. I am going to go through, for those who have not seen these figures, these slides very quickly, so I apologize in advance. These are all public. You can talk to me afterwards. You can see them. They're all online. But I mainly want to spend our time today talking about this particular roadmap and really getting into the meat of opportunities for reforms and solutions. And I think you'll continue to hear as these next presentations go on some more of these ideas. So for those who have followed the interconnection issue over the last decade, I think it's not a surprise that there has been a substantial increase in the United States in the number of requests, both in terms of individual number of requests, but also in capacity over the last 10 to 15 years. And that's what we show on this graphic. I think Charlie yesterday poached one of the graphics, the one that you guys can see on the left side here. And it's really substantial and pretty amazing to see that the active number of projects in the queue over the last 10 years has quadrupled in the United States. And so it is above 2 terawatts. And this is not a problem or an issue that is unique to any one balancing area or transmission provider. This is really seen across the board. I only show the ISOs, RTOs in the US on this slide, but we see this in non-ISO RTO balancing authorities as well. Now, this could be, a really great news story. We're trying to decarbonize the grid. There's a lot trying to connect on the grid that, implies a lot of economic activity. But with our analysis, we've also only seen about 1/5 of those projects that tried to apply, at least prior to 2018, getting inevitably connected to the grid. And so one consequence of that is high withdrawal rates, and that can lead to restudies for projects that remain in the queue, increasing uncertainty, both in terms of timelines, but also in terms of costs. And so that's what we're going to get into now, in terms of how we at least think about evidence of a problem. We don't necessarily see the withdrawal rates per se inherently as evidence, because you can imagine if you're trying to apply a bunch of terawatts, but only a fraction get in, as long as you have a bunch active, then you're somewhat successful. But it's really these next 2 metrics that we really believe provide evidence of a problem. So the first is that the study duration process is increasing in many regions. And that's what you can see on average in these black lines. 3 years on average for the study process in a lot of locations. Notably, there is variability both within a given ISO region as well as between regions. So ERCOT in Texas in the Southeast, at least the study process has shown signs of going quicker. We'll get into this a little bit, but this talks or speaks to potentially some of these connect and manage type of processes where congestion is being managed in real time in these processes or in these particular ISOs or regions, and therefore they're potentially saving some time on the studies. But it is important to make this point, which is that we don't just care about how long the study process is taking. We obviously care about how long it takes to get on for a commercial online date. So that's what this shows, is the period of time between an interconnection agreement being signed to a project ultimately coming online. And so some of this is outside of the discussions we'll mostly be having today, about the interconnection process. There's procurement issues, supply chain, amongst a slew of things. So it is important to keep the interconnection conversation in context to some of this larger whole. Okay, so second evidence of a problem is that we have been seeing via parsing a lot of the interconnection studies in these different regions that costs have been growing over time. That's for completed projects, projects that are still active in the queue that have some studies coming out, and maybe most importantly for withdrawn projects. And the graph that I show up here, these are average costs over time, but we've also noticed that the standard deviation, basically the variability of the costs within these studies, have also dramatically increased, which leads to a lot of uncertainty about the outcomes of the interconnection process itself. And that uncertainty is also one of the key problems that a lot of people are talking about. So I'm not going to talk about everything on this slide, but it's mainly to make the point that we're dealing with a multifaceted problem. There are obviously a lot of reliability and technical issues. We've been hearing a lot about that today, and Babak's presentation talks about some of that information. So that's obviously part of the challenge here. But I think the general sentiment that we've started to see is that we were asking the queue process that was originally designed in 2003, though has been reformed over the last 2 decades, but we're still asking it potentially to do too much. And it's related to challenges of transmission expansion. It's related to the need to use this process to get data collection and create certainty for project developers. And then there's a lack of standardization across different balancing areas. There's low consideration of grid enhancing technologies, which we learned about yesterday on a panel. And so we're in somewhat of this vicious cycle when it comes to how we are managing the queue process. Okay, so with my remaining time, I want to get into the I2X program at the Department of Energy and to talk more about this roadmap. So the Department of Energy kicked off this initiative about 1.5 years ago, and the mission of the initiative is to enable a simpler, faster, fairer interconnection of clean energy resources while enhancing and maintaining reliability. And there's 4 main pillars here. Those are outlined on this slide. There's a big stakeholder engagement pillar. Maybe some of you have participated in some of these discussions with different solutions exchanges that we have formed to try to address or raise to the top solutions to the problems that I have outlined. There's a big data and analysis component. You saw a lot of that in my prior slides, but that's a big component of this program. There's the strategic roadmap, which is what we are talking about today. That's what I'm going to talk about for the next 10 minutes of my presentation. But there's also a robust technical assistance program that the Department of Energy has managed. And a key thing to mention before moving on is that this project or program is both distribution system and bulk power system focused. I am here in my capacity as the bulk power system person, but there is a wide team of folks for those who are interested also working on distribution system issues that I can happily connect you with. Okay, so let's set up a little bit of the context and the purpose of the roadmap. How do we think about how we want this roadmap to actually engage in the discourse? We really are aiming for this to be a starting place for discussions. This is a very complicated, there's a lot of opinions on this particular topic, and it can be complicated to navigate and complex to navigate all the different solutions and ideas that have been thrown around and that are being proposed from different ISOs. You'll learn about what CAISO is proposing here shortly after me. And so with this document, we're really aiming to harmonize, collect, and develop novel solutions that provide a comprehensive and holistic look. So not just looking at queue management issues, but also looking at technical issues. So not really a piecemeal set of reforms. The way we think about this is the solutions that we identify, they're a collection of viable strategies that should be considered and discussed. It's not really a rigid package of prescriptive fixes, and that's in part because of this last bullet on the slide, is that there's a lot of regional heterogeneity. So some regions are further along in their reform process, for the interconnection effort. Some have adopted these ideas already. And so we try to highlight some of those efforts in the roadmap where possible. But we really wanted this document to be a comprehensive look at reform. And so just a few more kind of ideas. Some of the ideas and solutions in here are complementary. I think these most apply to some of the data transparency items that you basically need multiple solutions adopted together to be most effective, while others are somewhat exclusive. Whereas if you adopt one or you think about adopting one of these particular ideas, you might avoid the need to adopt another. So I'm not going to spend much time here because I think Rob is going to spend more time talking about FERC Order 2023, but I did want to put it in here as it pertains to the context of the roadmap. So as we were writing this document, FERC issued a very important order back in July of this year that worked towards, for folks who were here yesterday, Allison Clements mentioned, works towards baselining a set of reforms across the industry in the United States. And so in the context of the roadmap, I think the first point to make is that interconnection reform is not something that is new. This isn't the first time that we've been trying to work on this. This has really been an ongoing process since Order 2003. There were some really big reforms that happened in the late 2000s with the advent of a lot of wind starting to enter into the queues. And so that historical context is important when thinking about solutions, and we try to include that in this document. The last thing to mention is that the roadmap contains some ideas and solutions that relate and align with that order. Some of them even explicitly talk about compliance, but we really aim to introduce some additional ideas, longer term thinking ideas that could support interconnection process evolution. Okay, so I'm going to spend a good amount of time on this slide to talk about particular roadmap goals, as that is how we have organized and structured the document, and that's how you should think about the solutions that we've come up with. So this first goal, which is near and dear to a nerdy person who works at a national lab, whose lifeblood is oftentimes data, but the first goal is to increase data access and transparency, importantly in a way that goes beyond FERC Order 845 and FERC Order 2023. And we think that in part, this transparency is needed to both facilitate screening and optimal siting of projects for folks who are planning on making an interconnection request, but also to facilitate automation of the process itself. But maybe most importantly, we really see the need for data access and transparency as a way to enable benchmarking, tracking, and ultimately auditing of a lot of the reforms that are going to happen over the next 2, 3, 4, 5 years and beyond. And we see needs for this transparency to really make sure we are making smart real-time decisions as we learn more about how the reforms are trickling through the process. So the goal number 2, which is definitely an important one, related to the evidence of the problem number 1 that we were talking about, is improving the process and timing of interconnection. So the key focus areas, for those that know the buzzwords in this domain that we talk about here, are queue management issues. We speak to affected system studies, as well as workforce development. And I would say a key trade-off and tension that we try to navigate with these solutions is balancing the likely need to ration queue space that is currently being discussed in certain ISOs and probably should be discussed elsewhere, while also maintaining open access and competitiveness, which is a key FERC regulatory mandate. So in the section, we talk about the development of fast tracks that could potentially be used, increased collaboration between neighboring balancing areas, as well as a focus with the workforce issues on expansion and retention. The next goal, potentially the most contentious goal, or at least some of the most contentious items within this section, is on promoting economic efficiency. So the key focus areas here are cost allocation challenges and issues, coordination questions between interconnection processes and transmission planning processes, as well as improvements to the interconnection study methodologies themselves, So this is where we're talking about proactive transmission, investment funding opportunities. We'll speak a little bit to these novel interconnection service options that we believe should be considered, like energy only, connect and manage, as well as including a set of best practice study methods and transmission mitigation options that we believe are needed to help unlock some of the backlog. The last goal, which is I'm not going to speak about really that much here, not covered too much. This was led in collaboration with some ESIG colleagues at Julia. And this one really focuses on some of the reliability and technical models, tools, and standards that we've been learning about over the course of the last few days. Really developing a foundation to manage these high penetration rates of inverter-based resources that we expect. So just two more slides here. I'm going to go through these somewhat quickly. There's a lot, of course, on this slide, but my main purpose is to give you a sense of the structure of these solutions and how we talk about them, and then obviously encourage you to review the roadmap once it comes out. So with goal number one, we come up with 3 different solutions that you can read here on the left side of the graphic related to enhancing the scope and quality of data on projects that are in the queue, enhancing accuracy of interconnection study models and substance that go into them, as well as developing different tools to facilitate transparency. So for those folks following the FERC order, this is ideas about the heat map. And then after describing these solutions, at the end, we basically build these tables where we outline different stakeholders that we believe should contribute to the implementation of such a solution and document certain activities that they could take to facilitate or contribute to the facilitation of these solutions becoming more practiced across different ISOs and RTOs. So in total, there are over 30 solutions that are identified in the roadmap. We're not going to go through all of them here, of course, but I am putting up a few more select solutions for goal number 2 on process and timing improvements, as well as goal number 3 on promoting economic efficiency. So when it comes to timing, we talk about these automation issues, we talk about surplus, generator replacement, and energy only opportunities that might be able to fast track certain interconnection processes. We also speak to longer term ideas like market-based alternatives to rationing interconnection space. On the cost allocation side, we talk about requiring or needing better options to allow connection of certain resources without paying for congestion. We talk about aligning interconnection and transmission planning processes and some of these other ones that I mentioned on the prior slide. So this will be my last slide, and it's mainly just a call to action or a call to have folks in the room who at least are interested to join us as we continue to work on these issues. This is a draft roadmap. It's going to be released shortly within the matter of days. And for those who are interested or have great ideas, we'd love feedback on what we missed, what the gaps are, because we really do want this document to be comprehensive. We're going to continue these solutions exchanges, so these stakeholder engagement processes into 2024, potentially on some of the ideas that we've outlined here. It would be great for you all to join on that. And then even beyond I2X, you know, we realize there's a lot of people working on interconnection, and we are trying to be additional. So we're always open to ideas on how, you know, we should and could be working on helping for the, you know, plethora of stakeholders that are actively making decisions on these topics day to day. So with that, I'll thank you and look forward to the discussion.
Thank you, Will. Thanks for that great overview of current status of the queue and some of these ideas of how we can improve things moving forward. I also really enjoyed the 3D maze you showed up there. I kind of had some memories of chasing my 3-year-old toddler through a corn maze in her Encanto dress. And I'm just glad that that was not a 3-dimensional corn maze as you described the interconnection process. So with that, we're going to move on to Danielle Osborn Mills to discuss some of the recent enhancements in the interconnection process within the California ISO. Yeah.
Thanks, Josh. Hi, everyone. I'm Danielle Mills. I'm with the ISO. Been there for about 6 months, so be gentle. But this is my first meeting at ESIG, and it's been really impressive and great to be a part of this. So thanks for inviting me, and thanks to Will in particular for the helpful setup. The California ISO is in the middle of our now annual interconnection process enhancements initiative. And this year is a year where we are all anticipating very significant and transformative changes to our interconnection process. And we were before FERC Order 2023 came out, but now we sort of are managing the two changes to our process in tandem. But one of the things that we've been thinking about, fortunately for the last several years, has been kind of teed up both in Order 2023 and in some of the discussion that we'll have today. And that is doing more transmission planning to help inform the interconnection process. And this is something that in California has been laid out in a memorandum of understanding between the California state agencies, the Public Utilities Commission and the California Energy Commission, and the ISO in December of last year to really tighten some of the linkages between how we do resource planning, transmission planning, and have that inform procurement activities, which then inform the interconnection process. And this is, very timely for us. We have just gone through a transmission process where we approved 45 different projects totaling over $7.3 billion. Many of those projects are designed to clearly to satisfy the procurement needs that are going to come out of the state and the need for a transition to clean power in California. But also a number of them are going to help reduce congestion within the state to help bring additional out-of-state resources into California. So this transmission planning process that we do annually is driving some of these new investments in the transmission system. And what we want to do now is make sure that the interconnection process really is fed from that, so that developers know where they're going to be most likely to be able to interconnect, and to provide a signal to the load serving entities to procure in some of these areas as well, because they know that those projects will have the highest likelihood of success. So this in and of itself has been transformative, at least within the ISO. I think that the rest of the stakeholders within the state are sort of adapting to this as we go, and it's going to be reflected in our interconnection process enhancements initiative as well. And it's also timely because we have seen just ridiculous surges in interconnection requests in the last two clusters. With cluster 14, we received a real spike in interconnection requests going up to 373 individual requests, bringing our total queue up to more than 185 gigawatts worth of projects. That's including some of the pre-existing projects from before cluster 14. And then in cluster 15, we signaled that we were going to need to make some of these significant changes and at one point contemplated delaying the cluster window. And so I think that the signal that sent to the market was to get their interconnection requests in quickly. So we had another surge where we received 544 interconnection requests. We actually did a survey ahead of time just to get a sense of how many we should expect, and it was roughly 300. So we've just been a little bit inundated with this amount of individual requests as well as the capacity behind them, and really need to find a way to reform our process so that we're able to produce meaningful studies that yield better information for the development community to go market their projects to off-takers. Just a note to kind of try to put some of this in perspective. The transmission planning process that we went through last year approved, I mentioned those 45 new projects. Those are meant to satisfy or to accommodate about 40 gigawatts of new power, which is anticipated as being needed within the state's planning portfolios. Right now, our 20-year transmission planning process assumes that we'll need roughly 165 gigawatts by 2045 to meet our SB 100 goals. And we now have more than double that in our queue right now. So it's not that these are projects, it's not that we need to move these projects out of the way, but we need to find a better way of sequencing and figuring out which of these projects should move forward in line with the resource planning that we're doing and the procurement that we're doing. So we've taken this interconnection process enhancements initiative in 2 tracks. Track 1 was approved by the ISO Board of Governors in May of 2023 and then approved by FERC in August. And that really just enabled us to continue on with a new schedule for the cluster 14 projects to get those studies underway, and made adjustments to the cluster 15 schedule so that we could make some of these transformative changes. So cluster 15 is currently on pause. We have those 544 interconnection requests just sort of sitting there waiting, and then we'll implement the changes, or we'll apply the changes that we implement from the interconnection process enhancements to cluster 15. And we're hoping to bring that to the CAISO Board of Governors in February of next year, which is a tight time frame. We've in this process, we've engaged stakeholders quite a bit. This is something that the ISO is really working on and trying to enhance. We've held a number of stakeholder working group sessions where we actually agreed on all of our working principles for the group, agreed on the problem statements around both interconnection request intake. So how can we avoid 544 interconnection requests for cluster 16? But also problem statements around our queue management procedures and what we can do to make sure that the projects that are currently sitting in the queue are able to advance to commercial operations or withdraw and not stand in the way of other projects that may be behind them. So we put out a straw proposal about a month and a half ago. We're working through more working groups. We just had one this morning, which regrettably pulled me away from a lot of you this morning, and are working on getting a draft final proposal out later in November. And then we had the FERC order come out in early August or late July. And this, I think Commissioner Clements mentioned this yesterday when she alluded to the FERC order being somewhat of a baseline setting. And to the California ISO, a lot of the new requirements in the FERC order 2023 are common practice for us. So we've been using the cluster study for about 10 years. We are trying to continue to transition to more of a first ready, first served process, but that has sort of been a part of our process for quite some time. And so we are working on our compliance filing, I think somewhat unique. We are working on complying as fully and as quickly as possible with this so that we can continue on with some of the changes that we had been contemplating in the interconnection process enhancements initiative that we're taking on. So because of that, we had this dynamic where we had a number of stakeholders proposing different ideas over the summer that the FERC order then came out and sort of set new requirements that made it hard for us to think through some of those proposals in the same way. So we're kind of clearing our plate a little bit by making sure that we're in compliance with this FERC order so that we can then use that process that's laid out in the order as our new blank slate and then make the interconnection process enhancements on top of that. So we had to take a number of things out of the scope of the IPE initiative, but are really focusing now, IPE is the Interconnection Process Enhancements Initiative, trying not to use that. We had to take a number of things out of that scope, but are really trying to focus that initiative now just on things that are really unique to California and acute to some of our issues. So with that, in our straw proposal right now, we are, as I mentioned, the really central piece of it is to implement the zonal approach, which is making sure that there's comfort and natural sequencing and ability to make sure that the development and the interconnection requests are focused in areas with available transmission capacity. So we actually set a requirement that for an interconnection request to be able to proceed as an option A project, which would earn rate recovery, they have to be located in these zones with available transmission capacity. Projects outside of the zones can still submit an interconnection request, but they have to go through a separate process that's more of a merchant-funded opportunity. So that's called option B. And we're, I think, generally getting some good feedback on this and some positive feedback on this, and it's helpful to see it included as sort of a best practice. I will say something that on Will's slide that really resonated was the importance of having really clear information going into this process. So we get asked very frequently from developers, we're going to know where we should interconnect, right? And where our interconnections, our interconnection requests are going to be approved and where they're going to have to be option B. And so we have to make sure that we're providing them with the right level of information to be able to slide into this new zonal approach. Once we have the interconnection requests in the areas with available transmission capacity, we plan to apply some scoring criteria. And this is really to evaluate the readiness of different projects. We're trying to make it as objective and clear and really simple as we possibly can. This is another thing that was, I think, noted on Will's slides. Having verification of this can be a really time-consuming process. And so we're trying to make sure that the scoring criteria that we have and the different sort of indicators of whether a project is more ready than another are easy for us to say, okay, yes, they have that permit, or yes, they have been shortlisted. And we're still really working through with the developer community and the LSEs, the load serving entities, what the right balance is there and how we can make sure that we're managing expectations of projects as they come into the interconnection request process, and not expecting too much, but still enabling the best projects to move forward. From there, we're also proposing an auction as a backstop mechanism. And this is really just in case everything goes as planned and we have very ready projects entering the queue. We may still need some way to kind of right size the number of interconnection requests that move to the study phase. And so an auction is a very clear and objective way of doing that. We are designing it in a way that is intended to reduce the ratepayer impacts and have actually the revenues from the auction go to support network upgrades and transmission projects. So that's one benefit of it, but this is definitely an area that we are refining right now as we're developing the draft final proposal. And then I mentioned we have this option B process for projects that may not be in zones with available interconnection or available transmission capacity. So we're making some refinements to that process as well, so that they can continue to proceed in that manner. Finally, and I think this is probably the stickiest issue that we have right now, is that we have a ton of new transmission approved but not yet constructed, and we have procurement requirements in the very near term that are going to be hard to bring online without that transmission in service. And so how we address that in the interconnection process in terms of allocating the right amount of transmission plan deliverability is really challenging. And that's something that we are working closely internally on, as well as with stakeholders. I think that the process that we use for allocating transmission plan deliverability is one area where we can address this issue, but there are other things that need to be done throughout the ISO and throughout the state to make sure that we're really resequencing the process of transmission development to make sure that it's there in time for these resources to come online. And then on the queue management side, we are really, as I mentioned before, trying to make sure that we're enabling the projects that are sitting in the queue to move forward, but we're also contemplating providing a one-time opportunity to withdraw from the queue and still receive their unused financial postings. And that would be, when we say one time, we really mean it. So this is not negotiating with my children. This has to be really a one-time thing. And so we're trying to find ways to make sure that that works and that we're able still to refund the revenues that were initially intended to go toward additional network upgrades behind those projects. And I think we've struck a right balance, but maybe refining that process a little bit as well. And then for the projects that are sitting in the queue, we are we're planning to set a more finite amount of time that they can remain in the queue. And if they want to continue to remain in the queue beyond that time, then they have to submit an additional financial posting. And this is really like to force a decision to either perform and proceed in arranging offtake and coming online, or to withdraw from the queue. And then there are a number of just smaller requirements around suspension rights and material modification, things like that, that we're contemplating as well in the initiative. This is our schedule if anyone is interested. We had, as I mentioned, a lively subgroup conversation today. We're moving at a very quick clip, but really feel very grateful for the responses and the feedback that we've received from the stakeholder community, and are looking forward to implementing something that hopefully is a little bit more manageable for all of us going forward. Thanks.
Danielle. Much better delivered child joke than my attempt to link corn mazes and three-dimensional mazes from Wills. Next, we're going to have Rob Gramlich from Grid Strategies talk to us about integrating transmission, interconnection, and RA planning kind of on a broader basis. So, Rob, please take it away.
Well, thanks, Josh. It's great to be here as always. Seeing a lot of friends from over the years. I think it's 20 years now I've been coming to these events. So thanks, Charlie, for your leadership, and great to see friends. I saw one old friend, Warren Lasher, out in the hall, and he was saying how it's great to dive into the details, but also sometimes zoom out a little bit and get to put some of these issues into a bigger context. And since we had 3 great presentations already, I'm going to try to not be redundant, especially because we do some work with LBNL and CAISO, and maybe try to put this into a little bit of a larger context. And I'm sitting here thinking to myself, we have a classic economic rationing problem. So think to yourself, if you're Taylor Swift and you have a bazillion fans who want to go to your concert in San Diego, and there's just way more interest than there are spots, what do you do about it? You could charge your fans $5,000 a piece. You'd probably piss them off, so that's tough. But what do? You put them, they could line up, and then first come, first serve. Or you could do some different services. You get some, special seating. Or they have like this movie thing that like you can go and watch the thing on a movie and not live. So that's kind of like energy only service, not network service. There's different service, I don't know, concert enhancing technologies that you could deploy. But I think we should think about this as a kind of classic economic rationing problem. And why is it such a rationing problem? Why is there so much interest? I think part of it is, Danielle and I were just talking, solar and storage, you can put those almost anywhere. So, and a lot of different types of people and companies can develop those projects. When it was all wind and natural gas, there was just a smaller set of entities that could do it or wanted to do it. And it wasn't so extreme. And the gas plants, back when I was involved with FERC, involved in writing Order 2003, the policy that set the current rules up in that year, 2003. And the only thing anybody was building was natural gas plants. And the system arguably worked pretty well for that. There weren't that many companies, and there weren't that many places where the high voltage grid and the pipelines crossed, where you would put a gas plant. And so it just wasn't that hard of a thing. But now you can do these almost anywhere, and almost anybody can do them. And of course, we are in the energy transition. There's a lot of growth in just the sheer volume of demand of new generation. So that's adding to the problem. And the fact that it's so distributed means that the old rules, and I'm the first to say this, the old rules that were written with natural gas plants in mind just don't work for today's resource mix. So let me dive into the content here and put it into a couple other economic and policy contexts, and try to get towards some solutions, or put some of these solutions into that context. First of all, constrained grid. Part of the problem is the studies are complicated. When you have a constrained grid, you have network upgrades deep into the system that the next generator in the queue might trigger. And if you have to do that sort of study and you have limited transmission capacity, the studies are complicated. They take a long time, and in most regions, the generator gets charged a lot, and then the generator gets assigned this high charge, and they drop out of the queue, and then you have the queue churn. So it's a lot of these point to the root cause of congestion, just like we have congestion in the energy markets, as shown on this slide. The upper right is the internal RTO congestion costs. You can see how those congestion costs have doubled the last couple of years, up to 12 billion for the inside the RTOs. And then this is the first time I'm going to use an LBNL slide, but not the last. On the bottom left is the interregional congestion. The darker red lines are the costs, and you can see that's high, and it has been growing quite a bit as well. So the interconnection queue is another form of congestion. And again, that's a lot of the root cause of the problem. This is the second of the LBNL slides. You can see over time in each region, the volume of projects is growing, and you can see the yellow is solar, the light blue is standalone storage, and the hybrid, the darker blue is hybrid storage. In other words, there is a lot of those plants, and again, you can put those almost anywhere. So we're getting a lot, and a lot of companies doing them. I think you've already heard we have a major log jam and problem, but those are some of the dynamics by region. There's a lot of metrics. We're starting to look at sort of who's doing this job well and not so well. And there's, sometimes projects in the queue or gigawatts stuck or years are raised. But, one thing is all of these regions have way more generation in the queue than the demand is in the market. And I think for the energy transition, we want to get projects through the queue. So I like to focus on the new capacity online. Unfortunately, that dropped in the last couple of years. So we need to sort of focus on how do we make sure we're moving enough projects through the queue to support the new generation that we need, support the state goals, the consumer goals, et cetera. So what's going on with transmission? And just two slides, sorry, about transmission planning. That would really solve the root cause. And unfortunately, on the right side, you can see the miles of high voltage lines has been dropping. We peaked around 2013. We had many ESIG presentations about MISO multi-value projects and ERCOT, competitive renewable energy zones, and others. SPP projects, that's what you see in 2013 when those got energized. But after that, we pretty much stopped as a country. A variety of reasons. That's for a different session on another day. We did this planning report card of whether best practice transmission practices are being used around the country. MISO and CAISO got a B grade. The others were well below that. So part of it is just we're not doing planning right. Across the top of this slide are those best practices that we think Brattle and Grid Strategies did this together. Proactive generation and load, in other words, plan for the anticipated future resource mix, do multi-purpose or multi-value planning, scenario-based, portfolio-based. Those are the essence of the FERC transmission planning proposed rule that Commissioner Clements mentioned yesterday that hopefully they will finalize in the next few months. In which we'll make sure that every region is getting an A or B at least on this transmission planning. But as and so this does address the planning and transmission infrastructure do address the root cause, but it takes a long time. So we can't do just that. We have to also focus on how are we going to fix the queue processes, as my friend Gabe Tabak at American Clean Power Association told me when we were talking about this presentation. He said, well, in the long run, we are all dead. So we need to work on the short term and fix some of these problems, get some things resolved in the near term. So with that in mind, I guess I'll echo what Commissioner Clements said yesterday and my colleague Julia Selker talked about on the Grid Enhancing Technology panel. Let's get the most out of the existing grid and deploy some of these technologies, including advanced conductors, because there's so many lines out there that need to be updated, replaced. They're so old. So if you're going to replace them, you might as well replace them with much higher capacity lines. So let's do these things that are much easier. They don't need 10 years of transmission planning or process or permitting. So let's do those things first. And then get going on planning. I mentioned MISO and CAISO are doing some good planning. You can, I don't want to get into too much detail, but those are some of the plans that they're working on in those regions. And then let's talk about specific interconnection approaches. You've heard some of these ideas, but I'm going to build it up chronologically through history. Sort of how did we get here? So first of all, these are all standard interconnection requirements across the country. It wasn't always that way. Prior to 2003, they were non-standard. Every utility sort of did its own thing. The Federal Energy Regulatory Commission, FERC, decided that just like it did for transmission service in Order 888 in 1996, it should standardize the terms and conditions of interconnection service. There were concerns about vertical market power. In other words, the transmission owner that also owned generation might favor its own generation connecting to the grid and disfavor third-party developers, IPPs. So standardized rules would ensure comparability, non-discrimination. So they started out, as I said, with putting into standardized terms through Order 2003. In that year, that included large generator interconnection procedures, large generator interconnection agreements. These concepts are still with us and being used. It was a sequential first come, first served approach. It allowed participant funding, this is important, which means the generator pays if it triggers that network upgrade, which could be deep into the network, could be hundreds of miles away from the point of interconnection. But it was sort of, I mean, there's a little bit of economic theory supporting it, but honestly, it was a political deal to get RTO, to get utilities into regional transmission organizations that FERC was unable to require, but they could entice utilities in by saying they could have the participant funding policy that most utilities wanted to have if they did that. The reason I mention it is it has been the source of a lot of problems in interconnection queues, because if you're the next generator in the queue responsible, you're the straw that broke the camel's back on the network upgrade need 300 miles away, then you get assigned this cost. It could be way more than the previous generator in the queue had to pay. And then you look at that price tag and say, well, forget about it, I'm out. And then guess what? The next guy in the queue gets that charge. And then everybody has to sort of get restudied, and there's this whole queue churn. Not every region operates that way. California doesn't do participant funding, but most of the other RTOs and ISOs do. So anyway, despite that, it basically worked okay over most of the years. We, by the way, followed up based on a lot of discussions at ESIG meetings. There was a lot of grid code talk in the mid-2000s because the wind generators were coming here, and again, the utilities were all telling them to do different things for their voltage ride-through, reactive power, SCADA, et cetera. Requirements, and so FERC standardized that in Order 661 based on an agreement with NERC and the wind industry. And again, ESIG, or at that time, what was that? Utility Wind Interest Group was working on that. So anyway, that was standardized. And then there were some evolutions over the years, which basically in 2008 there was around, in 2012 there was around. There was a lot of basically almost all wind in the queues, and that led to at each phase it was sort of a ratcheting up of the requirements, getting a little bit harder, a little bit more costly for the generators to get in. I hate the term speculative project because all generation projects are speculative until they, are actually built and under contract, but the idea was to make sure that the sort of the more serious developers or projects would go through, and it would whittle down or ration the interconnection capacity somewhat. So anyway, there were two rounds of that in 2008, 2012, and then 2018, another round in FERC that became Order 845, initiated by a petition that when I was at the American Wind Energy Association, we petitioned FERC for interconnection reform. FERC agreed. It became FERC Order 845. There was a little bit more flexibility, a little bit more transparency. So a lot of these same ideas that we're working on now have been evolutionary, and we've been moving in this direction. You've heard about Order 2023, which is, so we're now present day. FERC just issued that. It did a few things, a cluster approach. So instead of that, project by project, it started requiring, even though I think most of the ISOs and RTOs had in recent years moved to this, it required clustering, group all the projects together, then it's a little bit less vulnerable where one individual project is the straw that broke the camel's back. It's a little bit more as a group, a little bit more stable, therefore, in terms of what you can expect when you enter the queue. There are withdrawal penalties. There's to speed things up, some requirements, transmission providers under enforceable deadlines subject to penalty. And you've heard about some of these technologies and some of the assumptions on battery operation and ride-through standard for inverter-based resources. So some of that is in there. Present day, as Danielle mentioned, for CAISO, a lot of these regional reforms now don't need to do these things because these are now like the baseline that everybody has to do. So things like site control could be pretty significant, including in California and other places that have not done those before. So that, you know, this order to 2023 could be pretty significant for that, but I don't know anybody who says that's enough, that does the job. So now we have to talk about, okay, what are the further reforms? You heard for Commissioner Clements yesterday say it was sort of 2023 was a start. We've got more to do. So a couple slides on the more to do. I think personally we should move to limit the scope to more shallow network upgrades, not the few 100-mile away deep network upgrades. That's for transmission planning, because there's so many purposes and uses of those assets for load growth, for reliability, resilience, congestion reduction, et cetera, not just interconnection. So do that in the planning process. Let's narrow the focus of the interconnection process to shallower, build the driveway, not the highway system. And then, and this is, I guess, the title of my presentation, so I buried the lead a little bit, but these separate processes really need to be integrated together: transmission planning, resource adequacy, resource procurement, and interconnection, of course. And they operate in silos in most regions now, but the more we can integrate them and have them operate together in sync with each other, I think the better off the whole process will be, and the interconnection process at the end of the line will be much smoother. Some more, getting a little bit more specific, some more flexibility in terms of options, an energy-only service that's more aligned with sort of how commerce works. I mean, wind and solar generators are used to being curtailed. It's okay to be curtailed sometimes. It's not the end of the world. So some energy-only service that reflects the realities of the market. Transfer of rights. Certain regions have what they call capacity interconnection rights. More curtailment and redispatch options, and then driving towards certainty is a big one. The generators really need to know roughly what they're going to get when they enter a queue. It can't be a total crapshoot. So there are ways to do that, some ideas there. And then rationing and prioritizing. Again, there's the Taylor Swift concert ticket thing. You could have everybody, click the button at the same time. That's probably not ideal. As there are more readiness requirements, but then there are limits to that too, because people like Danielle would have to sort through with different companies and lawyers about did they really meet this milestone or not. So and then study assumptions, automation, these are all very promising. Will mentioned some of these, so I think generating a lot of these ideas, feeding into the RTO processes. Hopefully something good will come out of that. And then on the right is just sort of, again, back to sort of basic economic problem of rationing a scarce thing. I think we're eventually going to have to get to some type of auctioning, price-based rationing, given just the sheer volume of projects in the queue and the quotas, the readiness types of things. I think will have their limits. Last slide, I'm going to wrap up. So this is where Danielle and I sort of sync up. Again, we are doing some work with CAISO, but I think the unique novel aspect of what CAISO is now doing is they are sort of preparing these zones to be able to accommodate a certain amount of generation. And then if you're the generator, you're going to go to that zone and basically what you're going to get. Now you're allowed to go way over here, somewhere that wasn't planned for, that's not prepared, but it's probably gonna be slower, probably gonna be more expensive if you do that. So this is sort of getting ahead of the game, proactively plan to accommodate a certain amount. Let's create, sort of a socket, and then people plug in to that. And they've, as she showed with her memorandum of understanding, since the California PUC oversees procurement, they kind of line up the utility procurement of power with these zones and direct utilities to procure an amount, and that ties into their resource adequacy regime. And then, of course, the transmission planning incorporates these zones, so they're transmission planning for a variety of purposes, but including making these zones able to connect a certain amount of generation. There is at this point an auction that's part of it. It's sort of auction to be studied and get into the next phase, which is, I think, the first time that's been done or proposed. But that's getting a new idea that could help ration in a fair way the limited capacity. So this is, as far as I know, the most that anybody has integrated resource adequacy, procurement, transmission planning, and interconnection. And they certainly have a lot of challenges with the CAISO queue, so it's all needed, but every region is having these same challenges. So hopefully some of this will be a model for others. So I'll leave it there.
Thanks, Rob.